Hello, my name is Darren Wen and I am an applications engineer here at Microchip. Today we are going to be talking about new developments in our PIC32 family and high-end applications from Microchip. PIC32 was launched in 2007 and provided existing Microchip MCU customers with a logical migration path to higher performance MCUs. One of Microchip's strengths over the years has been the ease with which existing customers can move up and down the performance curve because of common footprints, peripherals, development tools and libraries. Unlike all other previous PIC MCUs which use proprietary cores, Microchip chose the MIPS M4K core for PIC32. The choice of core is largely transparent. Whilst the choice is generally not important, it is good to know what the processor at the heart of the PIC32 is capable of. By choosing the MIPS core, Microchip was able to tap into a high-performance product with a 20-year pedigree, offering outstanding performance for our customers. The M4K core delivers the highest drystone benchmark score in its class at 1.56 drystone MIPS per megahertz, and this can be demonstrated in our silicon. With a maximum operating speed of 80 MHz, this allows the PIC32 to outperform many competitors running at 100 or even 120 MHz. The Harvard architecture with separate instruction and data buses is true to Microchip's heritage, yet the unified address space with up to 512K of flash and 128 kilobytes of RAM provides ample space for even the largest embedded applications. Additional features include a hardware multiply and divide unit, JTAG debugging option, and a shadow register set that provides an additional 32 working registers for use in fast interrupt handling. Alongside the M4K core, Microchip have added a bus matrix that segregates the core from the lower speed peripherals, saving power and keeping a high throughput. For example, if your design needs a 9600 baud UART, why clock that peripheral from an 80 MHz source? Instead, slow the speed down and save power. It is unfair to select specific markets and applications for PIC32 because, like most Microchip PIC MCUs, they have wide customer appeal. However, the applications shown here are typical of where PIC32 is being used today. For example, in the home market, PIC32 is being used in intercoms, energy displays and a variety of audio devices. In the industrial arena, PIC32 is being used for user interfaces and communications hubs. And finally, in the automotive marketplace, we see applications such as fleet tracking and in-vehicle entertainment systems, and these are just some ideas of where PIC32 is used today. The initial range of PIC32 MCUs were launched in 2007 and offered twice the program memory and twice the MIPS of our largest existing 16-bit MCUs. The high-performance 80 MHz core allowed our customers to expand into new application areas. They were available as the PIC32 MX3 and the USB-enabled PIC32 MX4. Common device footprints, peripherals, and a common IDE and development tools meant that many of our 16-bit customers elected to migrate to PIC32 when they required extra resources. The second phase of the PIC32 series, the MX5, MX6 and MX7, were added in 2009. These new parts were focused on the communications arena, and they further extended the family and introduced CAN and Ethernet peripherals to the range. In addition, RAM was boosted to 128K in order to more readily accommodate all of these new peripherals. In early 2011, reduced memory versions of the MX5, 6 and 7 were released, allowing customers to cost optimize their designs. And finally, at the end of 2011, the new PIC32 MX1 and MX2 devices were launched, and you can expect to see many more releases in the future.